So dynamic logic. So we will see how we save the power from the pseudo MOS. So we evolved from the static CMOS logic to pseudo MOS. By having that, we can reduce the input parasitic capacitance. It has the potential of a faster logic evaluation. But the problem is PMOS device that is always on. So we made it temporarily enable that one by having clocked the PMOS gate there. So when the pull down happens, disable this PMOS by have a clocking. The timing is shown here. So we use the two different phases of a clock. One is pre-charge, and the other one is evaluation. So when the clock is low, the PMOS is on. So upload is pre-charged to VDD. At this moment, the input A is always disabled. So A is low, so phi goes low, the output is charged to VDD. Once the evaluation happens, we assert the proper value of the A, and then depending on the A, the output will go to discharged or stay high. So this kind of operation is repeated, pre-charge evaluation phases repeat again. By having this, we can make it faster evaluation without having any static power. No static power. So this is called the dynamic logic. The dynamic means because we are relying on the floating capacitance. The output load has the floating state. So we hold the value onto the capacitance, parasitic capacitance. But for the other two cases, static logic and pseudo MOS, there's no cases of having output load just floating. So we are using this kind of a floating output load capacitance condition to make it the faster evaluation. So in the previous example, we just had this clocked PMOS and MOS for evaluation. But what happened when the pre-charge happened, if the pull-down network is on, then the pre-charging it would not be properly done. So we add a putting device at the bottom so that the evaluation always disables. So when the clock is low, then pull down pass is completely disabled no matter what the input A is. So we prevent this pull down network to be on when we do the pre-charge. So typically dynamic logic constructed by this kind of arrangement. So phi, PMOS and MMOS at the top and bottom, clocked by the phi, and input network, pull down network only exists onto here, right? So we are not using the PMOS network. So PMOS is very inefficient for logic evaluation because it adds more input capacitance. So we only use MOS pull down network for this kind of a dynamic logic arrangement. Let's find the logical effort. So for the dynamic So this is a summarization of all these different NAND 2 and NOR 2 as well. You can calculate the logical effort there. Definitely is a lot smaller than the standard CMOS. Okay. In this case, why we are not calculating the logical effort for the pull-up? Because the pull-up is done while you are doing the pre-charge. So this kind of dynamic logic only activated for the pull-down network. The pull-up is done by pre-charging, so we don't need to calculate the pull-up logical effort. So we saw that in the previous example, the dynamic logic is a lot faster than the standard CMOS, but the problem is it requires input monotonicity, meaning it always requires the input for the NMOS pull-down network. Input must be goes from 0 to 1 or 0 to 0, something like that. This pattern is only required. If the input transition from 1 to 0 during evaluation, you will not recover from that wrong calculation. For example, when the pre-charge happens, if output is charged too high and start evaluation using the clock, assert the clock. Now at the time the input is high, so it evaluated to the pull down, but somehow this input is wrong, so it adjusted to the low, but there is no way to go up again because there's a pull down already happened. The pull up is not engaged, so there's no such kind of operation is possible. So this output logic evaluation is wrong. So we only allow the input transition from 0 to 0 or 0 to 1 or 1 to 1 staying high, something like that. Only 3 kind of input combinations allowed. So we cannot allow the input transition from 1 to 0 during evaluation period. This is kind of a very tricky condition. So how we avoid this? Let's see, if we just cascade those kind of dynamic logic, then what will happen? Let's see that first. Let's say if we have a cascade 2, this inverting 2 stages of dynamic logic. Let's say assume output is high. That's the pre-charge and evaluation signal comes in. When the input is high, stay high. The first stage output during pre-charge staying high, right? The pre-charge during evaluation output will be what? Because the input is high, during evaluation X will goes down. What about the Y there? Because of that one momentarily it was high, the Y also goes down, right? During this time, because the input is stayed high momentarily, so you cannot go. But what it wants is that we want to evaluate for this low input, so we want that Y to be stay high, but actually it goes down. So this kind of a very narrow vision of this kind of wrong operation. So we cannot protect the output Y to be stay high. So we want to avoid this kind of dangerous spot. To prevent this kind of a problem, what we have to do is that we add the inverting stage here, so that during pre-charge the W is always high, and X is go to low. So input network here is always disabled, right? So the momentarily the input staying high was disabled. So when the input, this is kind of timing diagram. We have pre-charge and evaluation period. When we pre-charge, the output W and Y internal node W and Y pre-charge to high, and also input to all the domino logic is always disabled to go to 0. So pull down is disabled. And then when the evaluation happens, depending on the A and B, the W goes down. Once W goes down and then X goes up, right? This is the result of evaluation. Depending on the A and B, X goes up. Now start evaluating on the second domino. The second domino evaluate the output. So the Y goes low and then Z goes up. So all the event here ripple through the change of A and B and the condition on A and B ripple through the domino by adding just simple inverter. So adding just simple inverter between the domino, we make we prevent such a wrong operation. So this guarantee the monotonic output transition. In symbol, also A and B, they clocked by the domino circuit, right? We add inverter, right? Here, when you add inverter, we better to use high skewed gate inverter. Okay, because meaning the threshold need to be a little higher. Threshold low skew. High skew means the having, let's say, if there is a glitch, let's say Y goes too low, so when the W goes low enough, then the it goes high. So the threshold make it threshold higher, probably. So evaluation faster, make it faster. If the output goes down, the inverter make a transition quickly. The domino optimization. So as you can see, that each domino gate trigger the next one. It's like the actual domino toppling over. So the gate evaluate sequentially, but the pre-charging is done in parallel. Every logic pre-charging, of a domino is happening at the same time. Thus, the evaluation is more critical than the pre-charging stage, and at the output we can make a high skewed gate, meaning we can size up the PMOS size so that when the output goes, what we pre-charge it to VDD, then if the logic discharging happen, then we can quickly make the decision by having high skewed gate there. So V out versus V in. Typical inverter, we have a half VDD as a logic transition level. VDD, let's say. We skew that to the higher side, so that if the input goes down a little bit down, then you can make a transition to the output to high, so we can boost up the speed, right? So typical domino perform only non-inverting function like AND or, because we added an inverter to guarantee the monotonicity at the output. So to have an inverted operation of the AND or an XOR, something like that, so we put it in like a two differential, like a differential structure. We use this kind of pull down network for the F function and the other one for F bar. So we have a true and complementary output at the same time, true and complementary. So for example, signal high and signal low here. So if the output goes to high, is the precharge, because when the precharge happens, the internal load charged to VDD and the inverter output will be 0. So if the output becomes 0, 0, it's in the precharging state, and also the input comes in, one of those two will stay high and the other one stay low. So the output will be evaluated. So either it can be 0. Let's just give it an example here. So we have, let's assume that we have a high and a low, and B high and B low input. So this is the true and complementary. So so think of like a low is A bar and A high is A, and B high is B, B low is B bar. Let's compute that A and B and A and B and each inversion. So for the pull down network, we know so we have A bar, AB. So through this series connection, we find through the inverter we have A and B, and parallel here, A bar and B bar here. Through the inversion, we have A and B, inversion of A and B there. So this is like a parallel and series combination, right? The pull down network generate the complementary output here. So by having this kind of a differential structure, we can get both at the same time, like an AND and NAND operation at the same time. This is the example of XOR and XNOR. Since the dominant only has the pull down network, so we have to write down the equation for like a function bar, right? So for example, for X or we know that A bar and B or A B bar, that can be written as a B or B bar and A bar or B. If you write down again A bar B bar or A B, like that, right? And also you can do the similar for the XNOR y equal a B or A bar B bar. We take the bar and bar, so a double comes out eventually a bar B or a B bar. So we can share the B bar and here and B bar and B here, right? Equation here for the pull down network. So starting with the B has the A, BA here, BA, and series or or B bar and A bar, B bar here, B bar and B bar and here B and A bar and B bar and B bar and A, right? This construct the what, the XOR, right? This part A XOR B bar, right? This portion, and then its inversion gives us XOR B. For the other path on the left hand side, also you can find out this is the A XOR B, right? So its inversion becomes XNOR B. So in this arrangement like this, we can pretty easily share the bottom pull down network, because domino only composes of the pull down network, so we can share some of the path to construct the pull down network. Okay. One of the problem with the domino is that it relying on the floating output nodes. So floating capacitor is charged to VDD, and if you wait long enough, then there's a leakage through the transistors. So that will discharge the parasitic discharge the charge stored on the parasitic capacitance. So we don't want that the charge to be leaked away. So what we can do is adding a keeper device here. For example, if the data is pre-charged to high, then inverter output will be driven to low, and small device PMOS device is turned on, so it will stay high. But this one should be weak enough so that when the pull down network is activated, we have to overcome this the strength of the PMOS, so we can and we can pull down properly depending on the A, right? So we usually put the keeper device very small or minimum device size, or even minimum device size plus and larger length. So L mean and L something larger than minimum value, right? In that way we can make it weaker, make it very weak, right? So they properly logic overcome that keeper devices. The dynamic circuit, they suffer from the charge sharing. For example, on the left hand side, the dynamic logic case, if we have the intermediate node X, which has a parasitic capacitance Cx, let's assume that we precharge to the Y VDD and the B is the 0, so this MOS is always off. In that case, if the A charged from A changes from 0 to 1 on the right figure here, Y, the Cx and Cy connected, so the precharged voltage on the node Y will move down a little bit, but it doesn't go down all the way to 0. And also the Cx also slightly charged up like that, so it doesn't go to all the way up to the, it doesn't go all the way up to the VDD, but it slightly charged to some non-zero volt value. So this kind of this kind of action happened because the charge on the stored on the Y discharged through the device, the MOS device, and it will dump the charge onto the CX. That's why the voltage on the CX goes up. This kind of charge sharing kind of issue, especially when you have a very large CX, compared to CY, then the voltage will go down a lot, right? So we have to prevent such kind of a problem. Otherwise, the inverter on the right hand side will, especially for high speed, we may make it skewed high skew inverter there. So if the voltage on the Y goes down slightly, it may trigger the inverter. So this is something that we have to avoid it. So the Cx and Cy will move to the similar voltage through the device A, right? The voltage we can find by the charge sharing, the initial charge on the initially the charge on the Cy, so it's VDD times Cy equal to Cx plus Cy, and the final voltage what would be. So this is the same as Vy prime, right? So that will give us the voltage Cy over Cx plus Cy times VDD. That's gonna be the final voltage we are seeing in here. So we need a Cx smaller. So this is something that we have found. We had found the equation. To prevent such kind of a problem, we used another secondary precharging transistor, so that we precharge the intermediate node to VDD as well. So even though the A is on, so B is off, then the charge sharing doesn't happen because this voltage intermediate node already charged to VDD. So during the precharge, the Y was also charged to VDD. So in the event of the A make a transition and B stay 0, in such case there's no charge sharing happen, even A is activated, right? So this is kind of the precharging circuit, secondary precharging circuit might require, right? As you can see, the dynamic circuits are very sensitive to noise because we are relying on the floating capacitance. Right? Such a floating capacitor or output very susceptible to noise. There are lots of noise sources. First, the capacitive crosstalk we had already explained before, and also charge sharing that I explained. Also, power supply noise and feed-through noise. For example, we have like a CGD, always the capacitor. If the input make changes, that will feed through will happen. The output will affected by that feed through capacitance, right? And lots of the thing more we can think of. So this is a very sensitive. The domino is very sensitive. So you have to simulate very thoroughly for all different cases and corner, and you don't want some signal nearby which has a very large activity. We don't want to put that nearby. But the domino is very attractive for high-speed circuits. It can be very faster. It can be 1.5 to 2x faster than static CMOS. So it has many challenges: monotonicity and leakage, and charge sharing and noise. But this kind of a circuit is used very currently widely used in the high-performance microprocessor like a CPU. It has arithmetic building block like a adder or multiplier or this kind of circuit require very high-speed operation. In that case, you may use that such kind of a dominant circuit. But nowadays, most of the ASIC design, we prefer robust operation rather than the speed nowadays, and we care more about the power consumptions, etc. So this kind of old days, we were competing the speed at the time of the building up the high-speed CPU. Nowadays we are more on the parallel processing, so we need like a low power multi-core processor to handle the data bandwidth and also the power consumption issues. Okay. The pass transit circuit is very widely used here. It behaves similarly with the CMOS standard CMOS static circuit. It doesn't have such complicated consideration like domino circuits. So we use pass transistor like switches to do some logic function. So now the input for the switch, we are at the input we are seeing the diffusion instead of the gate, right? So let's find out the example like a transmission gate like this. We have a pass transistor here, 1 and 2, transmission gate here, PMOS and NMOS in parallel. So this kind of, we have a selection signal for NMOS and PMOS shown here. It just implement the multiplexer, right? The problem with the multiplexer using the transmission gate is that any noise on the input will pass through and to the output. So to avoid that, we add the inverter at the output of the transmission gate logic here. So we have in that way we can restore the value with the new supply and ground signal, right? So gate should be another inverter or gate will be added at the output. So this kind of implementation is simple for like implementing transmission gate. So mostly the transmission gate, the multiplexer implementation, we use this kind of pass transistor circuit typically. This is a lot simpler than the the gate level implementation, right? Lean integration with pass transistors. We can remove the PMOS transistor to make it simpler. In this case, MOS threshold voltage better to be small threshold voltage. So that the voltage drop will be minimized. You know what the problem with MOS is, that it cannot drive the logic high all the way up to the VDD. It only goes up to VDD minus VTH, right? So we want that VTH is smaller, and also having keeper device is shown here. When the input goes slightly high, then low skew inverter make a transition to low, that will trigger a PMOS on, then that will go pull up the input of the MOS. It will go all the way up to the VDD here, right? By the action of the keeper device. So we can add the weak PMOS feedback to pull the input of the MOS inverter to the high voltage VDD. So this here is very critical. For the ratio is critical, because this PMOS keeper device would need to be weak enough so that the MOS driving here. So typically the inverter will drive through this device. So this MOS and the pull down device at the same time need to be stronger than this PMOS device, right? So that we have to make it, the PMOS keeper device should be small enough. And also the low skew device, the size of the PN ratio need to be adjusted so that the MOS is greater than, so like this MOS ratio, instead of the 2:1 ratio, to make a low skew device, and we make the MOS device larger, so that the input it goes up slightly. This one win over that PMOS, so that the pull down is happen faster than typical 2:1 inverter. So this kind of low skew device, we have to make sure that all the corner and process variation, this kind of arrangement need to be properly operating. So we have to double check always. CPL is the complementary pass transistor logic. So we put some the previous the leaf circuit in two. So apply the complementary input, and we get the complementary output by having this kind of a dual structure. For the keeper device, in the previous case we had like this feedback, but because we have internal the negative value in there, so we can add this kind of arrangement for the keeper device at the input, so that it doesn't load up. So the output load will not see this keeper device parasitic. So we can have this kind of a cross-coupled keeper device in here, right? This kind of things avoid ratioed feedback, because we can have if the one is high and the other one will be low. So if the other side is low, then this PMOS is on, so the high value will go up. So this is the little low high will be go to the fully VDD by this pull up PMOS.